All right, well, let's start with our advice. It's the same advice as before. If you want to do well, make sure you do problems. These are practice problems. There's another set of practice problems from last semester, and we'll send a link to those. And the more problems you do, the easier it gets. Now, in some sense, this test should be not too bad because there's not a lot of stuff that we can test from, because we've only had a couple of weeks since the last exam. So that means you get to really focus on a very small set of topics. On the other hand, well, you haven't had that much practice with these topics. So there's balance between these two ideas. But I hope you'll do well. I'm optimistic you will. Of course, number 2, take care of your health and make sure you get plenty of exercise, enough rest, and as always, that includes mental health. Now, before we actually start the problems, I do want to talk a little bit about antiderivatives and the process. So when I'm trying to solve a problem that involves taking integration, which basically for me means a problem that says, let's look at antiderivatives, what I do is I run through more or less a couple of basic checks. The thing I first see is this one of the basic 8 things I can do? And when I say the basic 8 things I can do, these are the 8 integrals that we know how to do. And this list is not going to expand very much. By the time you hit Calc 2, it'll be at 10. And that's it. That's your whole life when it comes to doing antiderivatives and integration. So we're looking for some of these integrals. If it's not one of these, don't try to integrate it. So what do? Well, rewrite using algebra or trig identities. Or look for substitution. Substitution is one of the most powerful tools you have when it comes to integration. And so what substitution allows you to do is essentially in both the algebra trig and substitution, the whole idea is let's rewrite this to something which is easier for us to digest in the hopes that what we have is going to be really good, much better to work with. You will note that there's a little star here which says when you're working with a definite integral, there's a few other things you can look for. Namely, look for symmetry. So, for example, if you have an odd function, you can get cancellation without having to actually do anything at all. Or look for circles, because then we can use geometry. And that's pretty much it. Pretty much everything that has to do with integration in our class is on this page. And so you'll be surprised how far you can get with just a little bit of knowledge. Of course, there are subtleties when it comes to substitution. There are subtleties when it comes to algebra and trig. But you get better at that the more you practice. And the more you practice, the better you'll get. So let's begin. We start with number 1. It's a very good place to start. So find the integral of 3 secant x tangent x plus 4x squared plus root x plus 5 all over x plus e to the 3x. Now, the good news is 2 of these pieces are pretty much freebies. The secant x tangent of x, that's on our list. E to the 3x, that's also on our list. Now you might say, wait a second, your list had only e to the x. We do say, look, e to the 3x, that we can handle. So if it's have a constant in your front of your x, that we have ways to handle that. This piece is not on our list, so we need to rewrite it. But the good news is it has something very positive going for it, namely these plus signs. Plus signs in your numerator are your friends, because plus signs say, I can pull things apart. So we're going to do a little bit of algebra before we actually do our integral. So we still have the 3 secant of x, tangent of x, and then here we'll put each term over x. 4x squared over x is 4x. Square root of x over x will become 1 over square root of x, but we write that in our calculus way. That's x to the minus 1/2. Then 5 over x. Now 5 over x you can write as 5 times x to the negative 1. But 1 over x is like a really special case, because 1 over x made our list. And we usually leave 1 over x as is. All right. And so what does that become? Well, we get, now we can just integrate. Integral of secant tangent is secant. It's on our list. So 3 secant x. Integral of 4x. Well, 4 times 1/2 x squared. Integral of x to minus 1/2. be x to the 1/2. So what are we doing here? We're adding 1 to our exponents, and then we divide by our new exponent. So in this case, we added 1, we got 2, divided by 2. Here we add 1, we got a 1/2. Divide by 1/2, which is the same as multiply by 2. 1 over x, it's on our list. It's a really special case, log x. Normally we don't test that you put absolute values, but technically you should. And then the integral of e to the 3x, well, that's e to the 3x, and then you compensate for the 3 by dividing by 1/3. And because this is an indefinite integral, and if you want the full points, make sure you put plus c. And if you don't put the plus c, you'll lose a point. Because the plus c is very important. It's going to be a useful tool as you go on and do things, say, such as differential equations. It lets you do wonderful different things. So I'm just cleaning up a little bit here. You don't usually have to unless it says to explicitly, so 4 times 1/2 is 2. I wrote x to 1/2 as square root of x. Didn't have to, but I figure, why not? Maybe it looks better for those algebra people. And we're done. All right, so that's a good warm-up. All right, so number 2. Find the integral of cosine theta over 1 plus sine squared of theta d theta. Now, of course, you always think about the process. Is this on the list? And the answer is no. So now you start saying, well, there's a lot of trig stuff going on here. Could we do trig identities? And that's the dangerous thing with trig. There's always another identity. There's so many things you can do. So don't get tempted to do trig identities unless you sort of say, okay, there's something that's clearly going to be beneficial. Because there's lots of things we could do. For example, sine squared, you can use the fact that sine squared plus cosine squared equals 1. But it's not clear that that's going to help us much right now. But one of the things that I often look for when I'm seeing a problem for the first time is substitution. Because that's sort of the most powerful tool you have. And when it comes to doing integration, substitution is going to get you farther than any other tool. So in this case, what I'm drawn to is I'm drawn to the fact that I see this cosine theta upstairs. Now, the reason I say I'm drawn to that is if you think about what substitution says, it says if you have something like f of g of x, g prime of x, dx, this can become the integral f of the variable u du, where u corresponds to g of x and du corresponds to g prime of x dx. So when you're looking for substitutions, there's really 2 places to look. You look for something on the inside, a function in a function, or you look for something that's a nice derivative. Now in our case, I recognize that cosine theta, that shows up as the derivative of something. And in particular, if I take the derivative of sine, I get cosine. So that's suggestive. So the fact that I see a cosine theta right here, and that's a nice derivative of a function, which also is showing up in my expression here, that suggests the following. We'll make a substitution. So the substitution will be u equals sine theta, then du cosine theta d theta. Now that's not a surprise. I mean, I'm choosing u because I see like something which could be a good candidate for du. So we make our substitution. Let's see if it helps. Cosine theta d theta becomes du. So I've taken care of everything on the top. 1 plus sine squared theta. Well, sine of theta is u. So this becomes 1 plus u squared. So after the substitution, we've gone it down to an integral of 1 over 1 plus u squared. And 1 over 1 plus u squared, it's on our list. It's a great function. It's a wonderful function. Some people think it's even the best function. Arctangent. So arctangent of u, and then of course we put plus c. Now, unfortunately, our problem is not done yet. Because we started with something that was expressed in terms of theta. So our answer needs to be a function also in terms of theta. Because we're doing an indefinite integral, we need to end up with a function. So the way we get to our answer is we say, well, what is u? And The answer is sine theta, so we replace it. So we get arctangent of sine of theta plus c. And we're done. We found our antiderivative. And so you might be wondering, these problems seem to be going pretty quick. Well, don't worry, we have some which will take us longer. But yes, there are some problems on exams which are not very long. Oftentimes we'll have something like, can you see the substitution? And once you see the substitution, the problem works itself pretty quickly. So one of the things you want to really start thinking about is, how do you recognize that substitution? How do you come to spot it? You got to sometimes lean in and listen to the integrals, because they're trying to whisper things. Like the cosine theta, that's trying to whisper to us, think about a substitution of sine. And so look at the integrals. And if you listen to them, they'll tell you a lot. They're pretty good. They're pretty good. Okay, let's try another problem. All right, number 3. Find the integral 0 to 1 of t plus the square root of 1 minus t to the 4th quantity squared dt. Okay, well, this is a couple things have changed. First off, it's a definite integral, so that's something definitely new. So our answer is going to be a number, not a function. Looking at this function right now, it's not on our list, which is okay. Almost nothing we're going to give you is going to be straight from the list. You're going to have to think about ways to rewrite it. Is there anything that looks like we can do to this? Any suggestions, things we can do? Substitution? Well, I don't know if substitution is right yet. Think through the process. It's not on your list. After that, what comes? So if you go back to the little chart we had, which is somewhere, it says, well, if it's not one of your basic integrals, think about algebra and trig. Algebra and trig are pretty good. So what does algebra have to do with this problem? Notice there's a 2. That 2 there means square it. And so let's square it. So if we square that, what do we get? Well, we will get the following. We'll get the integral from 0 to 1. And so think of this as like a plus b being squared. So be a squared, that's t squared, plus 2ab. So that'll be plus 2 times t times the square root of 1 minus t to the 4th. And then plus b squared. Well, when we square the square root of 1 minus t to the 4th, we'll get 1 minus t to the 4th. Now, you might say, and if you hang out around me often enough, you'll say, well, Steve, I'm really skeptical about that last step. Technically, if you square a square root, you might say, shouldn't there be an absolute value? No. We're definitely, look, we're between 0 and 1. So 1 minus t to the 4th, always positive. No worries. No worries. Now, looking at this, we have some things that we're like, okay, we can handle parts of this. And then we have one part, this middle part, that's not so clear. So here's the nice thing about integration. See, in integration, we can pull things apart. So you can say, well, let's pull it apart. Some things that we can handle, no problem. And then something, let's think about a little bit more. So we can write this as the integral 0 to 1 of t squared plus 1 minus t to the 4th. So these are the pieces that look like a polynomial. That we'll pull apart. We'll do those okay, no worries. Plus integral 0 to 1 of 2t times the square root of 1 minus t to the 4th dt. All right, let's do the first piece. Integral of t squared plus 1 minus t to the 4th. It's 1/3 t cubed plus t minus 1/5 t to the 5th. So in other words, we're finding the antiderivative, and then we're going to evaluate from 0 to 1. All right, and we'll keep going in the next step. This other part, though, it's going to take us a moment to think about what to do here. 2t squared of 1 minus t to the 4th is definitely not on our list of things we know how to integrate. So that gets us into trouble. So we can't just be like, this is easy. So we have to start thinking about things that we can do. We've pretty much tapped out as far as algebra goes. I mean, there are things we can do. We can move the 2t on the inside, but I don't think that would help us much. Well, yeah, you got to be careful with square roots. Square roots are a dangerous thing. Square roots have lost more points for calc students than just about anything else. So let's remind ourselves of what we can't do. So if you ever have a square root of a squared plus b squared, it's really tempting to say, that would be really cool. It must be a plus b, because that would make my life easy. Well, I know that I say calculus is trying to make it easy for you, but this is a case where it's not going to work. So you have to be really, really careful with the square root. Now, at this point, let's think of a substitution we could make. Now, I claim that this problem is suggesting a substitution for us, if we listen to it. If you look for someone has suggested t squared. I see this 2t sitting here. That 2t sitting there works really nicely if I think of that as the derivative of t squared. So let's put a substitution, u equals t squared. du would become 2t dt. Now, not every substitution works, but we should try it. And worst case scenario, it doesn't work. And then we try something else. So the 2t dt becomes our du. The square root of 1 minus t to the fourth. Well, you got to think of a way, how can I write t to the fourth in terms of t squared? It's t squared squared. So this becomes square root of 1 minus u squared. Now, you have to be careful here. And I know that not everybody has caught up to the point where we're talking about substitution with definite integrals. So I want to be careful and explain what's going to happen, because we haven't finished the substitution yet. Because here's what's going on. Notice that this has bounds. See, these bounds, 0 to 1, those are the old bounds. See, these are bounds for t. And what's happening here is these are really t equals 0 to t equals 1. So whenever you see bounds, they are naturally associated with the variable. When we go to our new integral, we want to update everything. That also includes updating the bounds. So what do? Well, we want to get to u equals something to u equals something. So we think to ourselves, okay, well, if t corresponds to 0, what is u? Well, it's 0 squared, which is 0. And if t corresponds to 1, what is u? 1 squared, which is 1. So our bounds are 0 to 1. But I want to be clear. It wasn't just that we copied our old bounds. It just happened that in this particular case, the bounds are matching. You have to always update your bounds and be careful. But the great thing about definite integrals is you never have to go back. So we're never going to go back to t with this integral. It's now always moving forward. Okay, so now let's go to our next step. So we come back to our first piece. Evaluate from 0 to 1. That means we take 1/3 times 1 cubed plus 1 minus 1/5 times 1 to the 5th. And then we're going to subtract 0 plus 0 minus 0. 0 is a nice number. We like to work with it. The last piece, what do? Well, it might look familiar. Remember that we said that when we're doing definite integrals, look for symmetry and for circles. Square root of 1 minus u squared, that's a circle. So what we can do is we can say, well, this integral here, I can say it's taking this function square root of 1 minus u squared, which is the circle in the first quadrant. I'm only going from 0 to 1, and I'm going from square root of 1 minus u squared down. So this is the area of 1/4 of a unit circle. And the good news is we know how to find the area of unit circles. In fact, we know how to find the areas of circles. it's pi r squared. So we need 1/4 of that. So we're going to have 1/4 of pi 1 squared. So we're using geometry to do this integral. Well, let's go ahead and finish up. Common denominator here would be a 15, so you have 5 over 15 plus 15 over 15 minus 3 over 15 plus 1/4 pi. And that would be 20 minus 3 gives you 17 over 15 plus 1/4 pi. And there's our answer. All right, good. That was more fun. Okay, next problem. Number 4. Consider the following table, which gives information about the function f of x at some point. So I have here's x, and here's f of x at various locations. And we want to use this information to approximate the area under the curve y equals f of x from x equals 1 to x equals 4. And we're going to do it twice. What? Oh, we're back. Good. A, we're going to use Riemann sums with 3 equally sized parts and using the midpoint in each part. And then B, using Riemann sums with six equally sized parts and using the left endpoints in each part. So, well, let's start with A. So notice we're going from 1 to 4 and we're approximating the area under the curve. So area under the curve, f of x, that's really saying find integral 1 to 4 of f of x. So we're after approximating that integral. So that's our thing we're trying to approximate. So I like to do the interval. So I'm going to draw, here's 1 to 4, and it says we're going to have 3 equally sized parts. Well, 1 to 4, that has length 3, so we split into 3 equally sized parts, 1, 2, 3, 4. All right, well, that's good enough. Now, what are the widths? Well, the widths of all these intervals are 1. All right? Well, okay. Now, that's important because, well, remember, what's the Riemann sum? A Riemann sum has the form, it's a sum f xi delta I. So the function at some point, that's like a height, delta I is a width. So we need to know the width. So the widths are all 1. And now we have to identify which point for each interval. Now in this case, we're told the midpoint. So where are the midpoints? Well, they're at 1.5, 2.5, and 3.5. Those are the midpoints. So what do? So our Riemann sum will look like the following. We're going to take the function, which I'm going to call, let's call this here g of x, just for reference. So g at 1.5 times 1 plus g at 2.5 times 1 plus g at 3.5 times 1. So the function evaluated at the point times the width. Function evaluated at the point times the width. Okay. And there we go. Now we actually have to do this. So g of 1.5, that's f of 1.5. So let's figure this out. So we plug 1.5 in, that becomes 3. Then we plug 3 in, so remember, because this is really f of 1.5. So when we plug 1.5 in, we get 3, which is this is really f of 3, and f of 3 is really 3. Then this is f of 2.5, and we plug a 2.5 in, we get 3.5. We plug 3.5 in, and we get 2. f of 3.5, well, that gives us f at 2. Plug in 2, we get 4. So we get 3 plus 2 plus 4, which gets us 9. Okay, so that's part A. All right. Well, let's do part B. Part B. Well, what's the difference? Well, now we have 6 equally sized parts. Okay, So that's twice as many. I'll draw a little bit bigger picture. If we're going to do 6 equally sized parts, we have to find where these places are. So it's like we took our original parts and we just cut them in half. So now we have 6 intervals. What are the widths? Or how wide are these? Well, the answer is they're each a half wide. All right, so now we have the widths, and the last thing is which points? We're going to go with the left endpoints. So the left endpoint says at 1, at 1.5, at 2, 2.5, 3, and 3.5. So we're going to have a lot of stuff to add up. So g at 1 times a half plus g at 1.5 times a half plus g at 2 times a half plus g at 2.5 times a half plus g at 3 times a half plus g at 3.5 times a half. So there's our Riemann sum. So we just have to evaluate. Okay, well, let's do this. Well, let's just work this out. We can just follow what happens. So when we plug in 1, plug in 1 the first time, you get 2.5. Plug in 2.5 the second time, you get 3.5. So this will be 3.5, which I'll write that as 7 halves. So 7 halves times a half. Plug in 1.5. Well, we can actually do that because we did it already for part A. That gets us 3. Plug in 2. Well, plug in 2, we get 4. Then 4 gets us to 1.5. So that would be 3 halves, 1.5. Then times a half. Plug in 2.5. Well, we already did that. That's 2. Plug in 3. Well, plug in 3, we get 3. Then plug 3 back in, we still get 3. So that's 3 times a half. 3.5. Well, again, we've done that. That's 4 times a half. So let's see what we end up with. We have 7/4 plus 3 halves plus 3/4 plus 1 plus 3 halves plus 4. Now, if I add 7/4 plus 3/4 together, that would give us 10/4. I think. Yeah, 10/4, which is 5 halves. If I add that to 3 halves, I guess 8 halves, which means that all this together is equal to 4. Then another 4 makes 8, plus another 1 makes 9. And then add 1.5, so we get 10.5 is the answer. Now you might say, wait a second, these don't match. Well, they shouldn't match necessarily, because what we're doing is we're doing different estimates. And depending upon how you go about approaching finding the estimate, you'll get different answers. Did I make a mistake?
I think you forgot to time 4 with a half.
Ah, I did forget to times 4 by the half. 4 times a half would get me to 2, which gets us to 8.5. But they're still different. Good. So my statement still remains the same. You should not be surprised these are different answers. The good thing is that they're in the ballpark of each other, because we're both trying to do the same thing. They're both trying to get the approximation. Now you might be wondering, which one is the better approximation? And the answer is we have no idea, because we don't know what the function is. And if you don't know what the function is, you can only say, well, these are various approximations, and they are what they are. All right. Next one. Find the area between the curves y equals x squared e to the 2x cubed minus 3x squared, and y equals x e to the 2x cubed minus 3x squared. Okay, so what is that? Well, it says that we have 2 curves out in space, and somehow there's area between them. So most likely what's happening is that there's some sort of places where they intersect, and we want to find that part right there. Now, this picture is very not precise because we don't know what these curves look like, not yet, but that's sort of the idea of what you see. So if you have a problem that says find the area between the curves, and you're not given any other information, where it says like, well, between these 2 locations, then what you have to do is you have to go through and figure out where does the intersections occur and use that to then proceed. So let's figure out where the intersections occur. So where do these curves intersect? So that would happen if x squared e to the 2x cubed minus 3x squared were equal to x e to the 2x, oh man, excuse me. Boy. Maybe I'm just getting a little bit emotional here at this problem. It's just so beautiful, this problem. But no, I just have something in my throat. Okay, Steve, there you go. All right. Now, looking at this problem, what can you do? We like to cancel the e to the stuff. Can we, and why can we do it? So we can just cancel out. Why are we allowed to do that, though? Well, we're dividing by the same thing on both sides, but there is a subtlety. Be careful. You can divide to cancel as long as what you divide by is not 0. Now, in our case, we're taking e to something. And one of the properties about the exponential function is e to something is never 0. And therefore, it's okay for us to do our division because we'll never be dividing by 0. So life is good. Okay, so that says they intersect when x squared equals x, or x squared minus x equals 0. Notice that I don't divide by an x, because x could be 0. So you don't want to do that. And then we get x times x minus 1 equals 0, which means our intersections happen at 0 and 1. All right, well that's good. Now we know where they intersect. The next question becomes, which one's on top? Well, to figure that out, we know we're going between 0 and 1. So the easiest thing to do is just pick a point between 0 and 1. Anyone have a favorite number between 0 and 1? 0.5, also known as a half. Yep. And we can compare these two, say which one is a larger value. Well, these end pieces match. So the e to the 2x cubed minus 3x squared will be the same in both cases. So which is bigger, 0.5 or a half squared, or just 0.5 or a half? Yeah, just the half, because if you square a half, you get a fourth, which is smaller. So this one is the one on the top, and this one is the one on the bottom. All right, so the area, we now know where they intersect. We now know which one is on top, which one is on bottom. So the area will be the following. And in some sense, this one is not so bad because they only intersect in 2 places, so it never swaps. There are cases where you might have something intersecting in multiple cases, in which case, well, more work. You've got to handle all the places where things intersect. Okay, so we go 0 to 1. We take the top curve, x e to the 2x cubed minus 3x squared. Then subtract the bottom curve, x squared e to the 2x cubed minus 3x squared dx. Now, I will say that this is a case where if we were to do these separately, say, for example, just the integral of x e to the 2x cubed minus 3x squared, we would get in trouble. We would be stuck. So there is sometimes benefit to putting things together. So I know there's this desire, let me pull things apart as much as I can, but there's also, you got to balance it out because sometimes you want to make sure you put stuff together because when you put things together, nice things could happen. So in this case, what do I mean? Well, you could rewrite this as the integral from 0 to 1, x minus x squared times e to the 2x cubed minus 3x squared dx. So in other words, using the fact that they both have e to the 2x cubed minus 3x squared as common, I can pull that out. Now, what can we do here? Yeah, it's not on our list of 8, which of course, not very surprising. But what we can do is we can say, okay, there's not really much algebra trig we can do, but substitution looks like a good candidate. In our case, we say, well, there's a really strong argument to be made to make our substitution be the 2x cubed minus 3x squared. because I have that as a function on the inside. So whenever you're looking for substitution, there's two things to look for. Look for the function on the inside, or look for something that's a nice derivative. Hopefully you'll find something that's both. But I think a good candidate is always to say, well, let's try this function on the inside. So u equals 2x cubed minus 3x squared. What would du become? Well, 6x squared minus 6x. And then that's times by dx. Now if we look, it's not quite what we have, but it's pretty close. So there's off by a factor of 6. That's easy to fix. The other thing is, one of these has, you'll see it's like x squared minus x versus x minus x squared. Well, that means it's off by a sign, or negative. But that's also easy to fix. So what we can do is we can pull out a negative 6 here, and this becomes x minus x squared dx. And now we're happy that x minus x squared dx, that's what we want. How do we handle the negative 6? Well, I like to handle the negative 6 by a process I like to call divide by negative 6. So divide both sides by negative 6. Negative 1/6 du is equal to x minus x squared dx. So this will become the integral x minus x squared dx becomes minus 1/6 du. And then we're going to get e to the 2x cubed minus 3x squared becomes e to the u. Now at this point, you probably are getting nervous and saying, whoa, there's a negative there, and we were supposed to find area. Something's wrong. Or maybe not. We're not done yet. What haven't we done yet? Well, we're missing something. The bounds. Got to update the bounds. See, these bounds 0 or 1. These are x bounds. X equals 0. X equals 1. We need to get new bounds. We need to get the u bounds. U equals something. U equals something. So, to figure out the u bounds, we plug in. Plug in 0. You're going to get 2 times 0 minus 3 times 0 squared, which means our new u bound is 0. Plug in 1. 2 times 1 minus 3 times 1 is negative 1. So it's going from 0 to negative 1. Now, if you're familiar with numbers, that's usually the opposite of how we think of numbers being. Negative 1 should come before 0. And so what we like to do is we like to swap, so we put the smaller number on top. But if you swap, what happens to your sign? So anytime you do a swap, that's a flip of orientation. Every time you change orientation, there's a negative. So that gets rid of that negative. So we get negative 1 to 0, 1/6 e to the u, du. And this happens to be one of our integrals that we can do. Yes?
So to find the u bounds, what equation do we plug into?
To get the u bounds, what equation do you plug into? The answer is the x bounds, you take whatever x is, and you substitute it into your equation for u. So if x equals 1, put an x equals 1 into here, and you get u equals negative 1. So we get 1/6 e to the u, evaluated from negative 1 to 0, which is 1/6. When you plug in e to the 0, you get 1. And then when you plug in negative 1, you get e to the negative 1, or if you like, 1 over e. And there's the area. And that is a positive number. Now, if we've got a negative number at the end, that would be a sign that we should go back and check our work. Because area is something which has a definite sign to it. It's a measurement, and measurements tend to be positive. So if you get a negative, check your work. Don't just be like, oops, I'll just throw a positive in here, and hopefully the graders won't notice. We notice. We see all. So be careful. Find all values of a greater than 0, so that 5 is the average value of f of x, which is 4x cubed minus 24x squared plus 34x minus 5, for 0 less than or equal to x less than or equal to a. So, average value. Now that's something we should know. What is the average value? There's a formula for that. So in particular, if I'm looking for the average value for a less than, well, let me use different symbols. I'll use alpha less than or equal to x less than or equal to beta of f of x. The average value is 1 over beta minus alpha, integral alpha to beta of f of x dx. So essentially what you do is you say, well, what's the total area of f of x from alpha to beta? And then say, well, I know what the base should be. It should be this length beta minus alpha. What should be the height of a rectangle which would have the same area? That's the average value. So if you see the words average value, then you know there's a formula for it. And you say, okay, let me pull out the formula. And now we apply the formula. We say, okay, we know what our function is. It's right here. This is our function. We know where our endpoints are. It's given to us. So we'll do the following. We get 1 over a minus 0, because our endpoints are 0 and a, integral 0 to a of our function, 4x cubed minus 24x squared plus 34x minus 5. So that's 1 over a, and this is a function that's on our list. Polynomials are on our list. And remember, we can always pull functions apart and do when there's being added and subtracted. So we just do them each individually. Integral of 4x cubed, that's x to the fourth, minus 24x squared, that would be minus 8x cubed, plus 34x, that's 17x squared, minus 5 becomes minus 5x. Then we're going to go from 0 up to a. The nice thing is when you plug in 0, you're going to get a bunch of zeros. So we plug in a. Well, what do we get? We get 1 over a to the fourth minus 8a cubed plus 17a squared minus 5a, which becomes a cubed minus 8a squared plus 17a minus 5. So I can just take everything divided by a. All right, so that is the average value from 0 to a. Now, we need it so that we have it as 5. See, you see this word 5 is. Is just another way of saying equals. So 5 equals the average value. So this needs to equal 5. Now, all that's left, I don't know if I should say all, that makes it sound easy, but the next thing to do is to solve for a. Now, whenever you're faced with a polynomial expression like this, you do what you always do with any polynomial expression, move everything to one side and just start praying, please let it factor, please let it factor. Now, you probably are like, it's better factor because this is not a quadratic. It's a cubic. And we don't know the formula for cubics. Now, quadratics, we always have that backup, the quadratic formula. There's no backup here. We're playing without a net. Okay. Well, what can we do? Well, there's a series of things you can do. One of the things, though, is there's a wonderful idea called guess. And if you're faced with this situation, I guess you're going to say, oh, look, they want us to find the answer. It's got to be something really reasonable. So let's just guess a number and see if it works. Like 0. 0 minus 0 plus 0 minus 10. Nope, that didn't work. Okay, is there another number? 1? 1 minus 8 plus 17 minus 10. Let's see, wait, hold on. That's 1 plus 17 is 18. Minus 8 minus 10 is also 18. Aha! 1, that works. Okay, good news. We've made progress. Now, how do we get the rest? Well, we know if 1 works, what that means is that a minus 1 has to be a factor. Right? Because 1's a root. So if a minus 1 is a factor, I just start thinking about, okay, I have to have a times this, gives me a cubed. So that says my leading term is a squared. I'll jump to the end. Minus 1 times whatever the constant is has to be minus 10. So that means the constant term has to be plus 10. And then I say, okay, well, how do I get the middle term? Well, how about let's think about a squared. Because this should be something a, right? So I get whatever this is times a minus a squared has to give me minus 8a squared. See, does that make sense? Yeah. Okay, so I need, let's just put a little question mark here. How's that for right now? We'll fill the question mark in. So the n terms are easy to spot because you can figure out from the leading and from there. So whatever the question mark is, if I multiply this out, I get question mark times a squared if I multiply here. Then I get a minus a squared if I multiply those terms. And that's got to produce a minus 8a squared. So what do I need? I need question mark minus 1, better be minus 8. Yes? So what's this number? Negative 7. Now, if you don't like this process, which that's okay. I mean, it's perfectly fine not to like it. What you can do is you can do long division. So you're like, wow, long division? It's been so long since I've done long division. Can you remind me? Yes, of course. After we finish solving it. Okay, the a squared minus 7a plus 10 factor.
Oh, wait, doesn't. Minus 5.
Minus 5 and minus 2. Yeah. We try to get things that work out nicely. And therefore, our solutions are 1, 2, and 5. And we should double check. Are they all positive? Yes, they are. And there's our answer. Now, going back, if you wanted to do long division, it absolutely works. No worries. You would take a minus 1, divide it into a cubed, minus 8a squared, plus 17a minus 10. And the goal is you always think, okay, let me work with the highest terms. I need to get a cubed, so I take a times a squared. That gets me a cubed. So a squared times a minus 1 would be a cubed minus a squared. Subtract. Minus 8a squared minus minus makes minus 7a squared. And then I still have the other terms. Okay, now the highest term is minus 7a squared. Well, to go from a to minus 7a squared, that better be minus 7a I multiply by. So minus 7a squared, good. Then plus 7a, subtract. So those cancel. Now you get 10a minus 10. Say, well, a times what gives me 10a? And the answer is 10. And I get 10a minus 10, and I subtract, and I'm happy. Remainder of 0. So that's long division. So you can either use long division or a little bit of reasoning. But you should suspect that if we're going to give you a question, the answers work out nicely. All right. Well, let's try another one. So find the derivative with respect to y of the integral y squared to sine of y x cubed over e to the x plus 1 dx. This problem is one of those straightforward, you either know it or you don't. Now, I'm going to go on faith that you're going to know it. So, but just in case you may have forgotten what's going on here, this is really fundamental theorem of calculus. I guess we should abbreviate it as fundamental theorem of calculus. So just remember, it's always fun. All right. So what does the fundamental theorem of calculus say? The baby fundamental theorem of calculus, I should just say the very basic one, says if I'm taking the derivative with respect to, and I'll use the symbol y. Symbols can be changed. It doesn't really matter. If I go from a constant up to y of some function, say f of x dx, then this becomes f of y. That's the fundamental theorem of calculus. I've just changed the symbols around. But that's what the fundamental theorem of calculus says. If you take fundamental theorem of calculus plus chain rule plus a few basic properties, then you get the following. The derivative with respect to y from, say, some function g of y to some function h of y of f of x dx. Well, what you're thinking here is that this h of y is sort of a function in a function. So it's acting as, I'm plugging in a more complicated thing into this expression. So the chain rule says, take the derivative of the outside part, which looks like this. So that's f, but plug the inside in, which is h of y, times by the derivative of the inside, which is h prime of y. Now that takes care of the top. For the bottom, you just do the same thing, but you subtract, because it's top minus bottom. So it's f of g of y times g prime of y. All right, so that's the fundamental theorem of calculus. And this problem is basically, do you see that? And if you see it, then it's a free points. Well, we like free points, and we always want to make sure we get the points, free or not. So for us, we say, okay, so this is our function f on the inside. So we start by saying plug sine of y everywhere you see an x. So we're going to get sine of y cubed over e to the sine of y plus 1. Then you multiply by the derivative of sine of y, and the derivative of sine of y is cosine of y. All right, now subtract. Now you go to y squared. So everywhere you see an x, put in y squared. So y squared cubed divided by e to the y squared plus 1, and then times that by the derivative of y squared, which is 2y. And at this point, you're done. Life is good. Now, the way you definitely don't want to do this problem is you don't want to try to find the antiderivative of x cubed over e to the x plus 1. The reason you don't want to do that is you're not going to succeed. Because it's very easy to come up with functions that you cannot integrate. It's one of the fun things that we do is we say, well, let's come up with a function that looks almost like something they can integrate, but they cannot. So that's why stick to those basic 8. If it's not one of those 8, don't even try to integrate it. So you have to do something else. You have to find a better way. All right. Next problem. Find the integral of e to the 2z divided by the square root of 7 minus e to the z. Okay. Well, clearly this is not on our list of 8. And I don't see much that we can do in the way of algebra. There's no trig involved. So, substitution. Well, looking at this, there's an obvious candidate for substitution, which is look for the function on the inside. So the function on the inside is this square root of 7 minus e to the z. And I really want to get rid of, if nothing else, I really want to get rid of that minus downstairs. Anytime you have addition and subtraction inside a square root or in a denominator, that is bad. Unless, of course, it's the arctangent. Then it's beautiful. But that's like the one exception. So you really want to get rid of that. So I'm going to get rid of it by making a substitution. If nothing else, that should clean it up. So we're going to have our inside function be our substitution. U is 7 minus e to the z. Then du would be minus e to the z dz. Now, at this point, the minus, we don't really care about that. But we have a problem. We say, wait a second, we don't have an e to the z. We have e to the 2z, which is not the same. So we need to think of a way to handle that. Well, we're going to drop some knowledge here. It turns out, this is a true story, e to the 2z is the same as 2 copies of e to the z multiplied together, or if you like, e to the z squared. So, now we may not have seen to do that right away, but the substitution is saying that's how you should think of it. Now, the reason we should think of it that way is we can do the following. One of our e to the z's will be joined with our dz. And now, if we do that, that handles our du, which is good. But then you have the question, what do you do with this other e to the z? Well, that's when we come into our relationship. We know that u equals 7 minus e to the z. That allows us to say that e to the z can become 7 minus u. So now we're ready to do the substitution. This e to the z becomes 7 minus u. That e to the z dz becomes a minus du, so I'll put a minus here, du on the back end. And then the downstairs, that square root of 7 minus e to the z becomes square root of u. This looks a little bit better. Now, you might say, not a lot has changed. We've gotten rid of the e to the z's, and we've gotten rid of that minus inside the square root. And you're right. Like I said, it's better. You know, it's still not perfect yet, but the good news is, where's the minus? The minus is here. And that's a good place for it to be. When we have things that are minus in the numerator, they're not in the square root, that says you can pull it apart into two pieces. So we can really say, aha, here's what we have. So we have minus 7 over square root of u, which I can think of as minus 7 times u to the minus a half. Minus minus makes plus. And then u over square root of u, well, that would be u to the positive 1/2. So this is a situation where, because of now where our symbols are, we're able to manipulate and pull things apart into two pieces, each of which we can integrate. These are both on our list. Something to a power. All right, so we go to our first one. So we have minus 7. Our new power, well, will be to the 1/2, because you take negative 1/2 plus 1. Then multiply in front by the reciprocal, or if you like, divide by 1/2. So I'm going to multiply by 2 over 1. Then the next term, add 1 to the power, u to the 3/2, multiplied by the reciprocal, 2 over 3. And because I want my points, plus c. And don't forget, we've got to finish up by going back to what we started with. Whenever it's an indefinite integral, you always got to go back to your original. So I'm going to replace u by 7 minus e to the z. So negative 14 times 7 minus e to the z to the 1/2 plus 2/3 times 7 minus e to, that's a 7, minus e to the z to the 3/2 plus c. And there you go. So this is some of the things that might happen with substitution. We might say, well, once you've made a substitution, parts of your expression might become parts of your du. Other parts of your expression you have to rewrite using your new variable. So be open to the possibility that you might have to do that. All right. Number 9. Find the integral from 0 to 3 of 2x plus the absolute value of 3x squared plus 6x minus 9 dx. Now, this integral doesn't look so bad except for one tiny detail. Absolute value. Absolute value is sort of it's a headache. It's not fun to work with. So the moral is, don't work with it. So you might say, well, how can you not work with it? It's there, right? Well, we're going to get rid of it. So how do we get rid of it? So here's what we do. We're going to say, let's figure out what's going on with this absolute value. So we have absolute value of 3x squared plus 6x minus 9. And what we can do is we can take our absolute value and we can turn this into something which piecewise, there's no absolute value at all. So that's how we deal with an absolute value, is we're going to transform it into a good piecewise function for us to work with. So I need to get a handle on what this is. Now, you'll notice that one thing we can do is pull out a 3. So that's x squared plus 2x minus 3. And, of course, as everything seems to happen in this class, these will probably factor. Well, does it? It does. It's x plus 3 and x minus 1. Okay, so what does that tell us? Well, it tells us that this expression is 0 at negative 3 and at positive 1. Because that's where I'm going to have 0 on the inside. And now what I can do is I can say, well, what's happening elsewhere? So if I pick a number between negative 3 and 1, say I pick 0, if I plug it in, I'll get 0, 0, negative 9, means that my function's negative here, But if I pick a big number like 1,000,000, well, then the leading term dominates, so it's going to be positive after 1. If I pick a negative 1,000,000, it's still going to be dominant, and it's positive before negative 3. So I see that I'm changing behavior at 1 and at negative 3. But I only care about 1. Now you might say, why don't you care about negative 3? Well, look where we care about our integral. I'm only going from 0 to 3. So we say, okay, all right. So here's what we can do. We say, all right, this expression 2x plus the absolute value of 3x squared plus 6x minus 9 will break into two possibilities. Before 1, which I'll say is between 0 and 1, this expression on the inside is negative, so what we should do is we should subtract it and then drop the absolute value. So 2x minus 3x squared plus 6x minus 9. Between 1 and 3, the expression on the inside is positive, so we'll just add it and then we'll drop the absolute value, 3x squared plus 6x minus 9. So we get that, if we clean up just a little bit more, it's minus 3x squared, 2x minus 6x is minus 4x plus 9. If I'm between 0 and 1. Then here we get 3x squared, 2x plus 6x is plus 8x minus 9, and that's if I'm between 1 and 3. All right, so that work allows us to do the following. It says, let's take this original integral, and we're going to split it up into two parts, 0 to 1 plus 1 to 3. Because we can always take an integral and break it into parts. And if you ever have a function which is defined piecewise, that's the natural thing to do, is to pull it into pieces, each piece of which is easy to understand. So, from 0 to 1, our function would be minus 3x squared minus 4x plus 9. From 1 to 3, our function would be 3x squared plus 8x minus 9. And each one of these is not too bad. So the first one will get minus x cubed. The integral of minus 4x is minus 2x squared plus 9x. Evaluate that from 0 to 1. Then add to that, we'll get x cubed plus 4x squared minus 9x. And that's going to be from 1 to 3. So we plug in 1, minus 1, minus 2, plus 9. Now that one we can actually do in our head. That's negative 3 plus 9, which is 6. Plug in 0, we get 0. So 6 minus 0 plus, we probably shouldn't do the 3 one in our head. Okay, 3 cubed, 27. 4 times 3 squared. Well, that's 4 times 9, which is 36. Then we're going to subtract 9 times 3, which is 27. Oh, we probably could have done that in our head. That turns out to be 36. Well, subtract, plug in 1. That's 1 plus 4 minus 9. So that's 5 minus 9, which is negative 4. So minus minus makes this into a plus. So we get 36 plus 4, which is 40, plus 6 more. That gives us a final answer of 46. And there we go. Okay. Woohoo! Making progress. Number 10. Let f of x equals ax squared plus bx. Given that when using Riemann sums with 3 equal-sized intervals to estimate the total accumulation, really it's just saying you're integrating f of x from 0 to 3. Using the left endpoints, the value is 5. And using the right endpoints, the value is 2. What are a and b? So this is about Riemann sums. So we have this f of x, and we're going from 0 up to 3. And we're going to be doing Riemann sums. So, okay, so let's think about this. We're going from 0 to 3, and we have 3 equal-sized intervals. So 1, 2, 3. All right. So when we use the left endpoint, the value is 5. So let's figure this out. Notice that our width is 1. So So when we're using the left endpoints, we would take f of 0 times 1 plus f of 1 times 1 plus f of 2 times 1, right? Because 0, 1, 2 are my left endpoints. This is going to be equal to 5. When we use the right endpoints, so that would be f of 1 times 1 plus f of 2 times 1 plus f of 3 times 1, because the right endpoints are 1, 2, 3, the value is 2. So that's what we're told. We're told that when we estimate using the left, we got 5. When we estimate using the right, we got 2. And the question is, what's our a and b? So remember that this function is not just any function, it's a function ax squared plus bx. So, well, let's actually figure this out. Let's figure out what are our functions. So the function at 0, well, that's 0 plus 0, 0. Function at 1 is a plus b. And the function at 2 would be 4a plus 2b. And the function at 3 would be 9a plus 3b. So we put those pieces in. So I'm going to take the first 3 of these and add them up. F of 0 plus f of 1 plus f of 2. If I do that, I'll have 5a and 3b. So 5a plus 3b has to equal 5. Then I'm going to take the last 3 and add them up. So that's f of 1 plus f of 2 plus f of 3. So if I add those up, a plus 4a plus 9a, that will be 14a. b plus 2b plus 3b will be 6b, and that's going to equal 2. So now we have 2 equations and 2 unknowns. Oh, that's great. We love 2 equations and 2 unknowns. We've been doing that all the time. And we look for ways to combine these. Now, one of the things we could do is notice that here the 3 and the 6 are pretty close to each other. So let's take this first equation and multiply it by negative 2. And the reason I want negative 2 is that will make that negative 6b. So I'm multiplying the first equation by negative 2, then we're going to add these up. So negative 6b plus 6b would be 0. Negative 10 plus 2 is negative 8. Now, the interesting part. Negative 2 times 5a is negative 10a, plus 14a makes 4a. And therefore, we come to the conclusion that a has to be negative 2. Once you know what a is, just pick either equation, doesn't matter, and plug it in. So, for instance, if I plug a into the first equation, I would say that negative 10 plus 3 times b has to equal 5. Add 10 to both sides, 3b has to equal 15, which tells us that b should be 5. And there's our answer. So this is really testing us, do we understand what Riemann sums are, and can we work with them? And then get to a point where it's like, okay, 2 equations, 2 unknowns, bread and butter, life is good, life is great. All right. Number 11. Given that h of x satisfies the integral from h of x to 2 minus x squared of t to the 6th divided by t to the 4th plus 1 dt is equal to x minus 1, determine h of 1 and h prime of 1. Now you'll notice it doesn't say find h of x because you're not going to be able to do it. This is one that even Wolfram Alpha, which is pretty good, would struggle with. And I don't think it could actually do it, to be honest with you. All right, so what are we going to do though? Because, well, we've got to find h of 1 and h prime of 1. Now, what do we know? Well, we have this relationship, so let's use the relationship. So what I can do is I can say, well, let's just plug in 1 and let's see what happens. So we plug in 1. Let's do the easy side. When we plug 1 into there, what do we get? 0. 0 is nice. So 0 equals, then we get this integral here, and I'm plugging in 1. So h of 1 up to 2 minus 1 squared, which is 1, of t to the 6 divided by t to the 4th plus 1 dt. Now, if I think about this function, t to the 6 over t to the 4th plus 1, I don't know exactly what that looks like. I do know it's going to be 0 at 0, and otherwise it's going to be positive. It's going to do something vaguely like that. I don't know exactly, but it's something. And this says I'm going to definitely end at 1. And so here's 1. So I have to figure out, where do I start h of 1 at, so that the integral from h of 1 to 1 of this expression equals 0. If I were to start at negative 1, the area would not cancel out. They'd combine. So it wouldn't be negative 1. So I need something where the total area is 0. Positive 1 would work great. In fact, it's the only number that works. Because if I want an area of 0, if I don't pick 1, if I pick something over here, I get area. If I pick something over here, I get area. So I got to pick, the only place where I get no area is if I have my start and stop match up. So this is one of those properties about integrals which is nice to keep in the back of your head. It says, oh, if I ever have my start and stop points match for the integral, I get 0 area out. So this tells us that h of 1 has to equal 1. Okay, so now we know one fact. So I'll put that over here. So h of 1 equals 1, h prime of 1 to be determined. All right, but at least we'll get partial credit because we found h of 1. Now we start thinking about, okay, I want to find something about h prime of 1, which means, what do we want to do? We better take a derivative. So we're going to take the derivative of both sides. And then after we take that derivative, we're going to plug 1 in, and we're going to see what happens. Now, again, let's start with the easier side. What's the derivative of x minus 1? Yeah, 1. Okay, so take derivative of both sides. And what do we get? Lo and behold, we get that 1 is equal to, for this derivative, we're going to get, well, what do we need? Well, all right, let's write down what we're doing. The derivative of integral from h of x to 2 minus x squared of t to the 6 over t to the 4th plus 1 dt. What tool do we need? Fundamental theorem of calculus. The fun tool. All right, so we're going to use the fundamental theorem of calculus. So this says what you do is you take the top function and you plug it in everywhere you see t. So you get 2 minus x squared to the 6. Divide that by 2 minus x squared to the 4th plus 1. Multiply that expression by the derivative of 2 minus x squared, which is minus 2x. Then we're going to add to that. We plug in the bottom function, sorry, not add, whoops, subtract, because it's top minus the bottom, subtract, plug in h of x. So h of x to the 6 divided by h of x to the 4th plus 1 times the derivative of h of x, which is h prime of x. So we're taking the derivative of both sides. Now we plug in x equals 1. Well, when we plug in x equals 1 to the left-hand side, we'll get 1, because it's always 1. So we get that 1 is equal to, here we get 2 minus 1, which is 1. So it's 1 to the 6 over 1 to the 4th plus 1, also known as a half, times negative 2. And then here we get minus, and then it'll be h of 1, but we know what h of 1 is. H of 1 is 1. So it's again 1 to the 6 over 1 to the 4th plus 1, which is again a half, times h prime of 1. So we can now solve. Well, yeah, we can do that. This will become 1 equals negative 1 minus a half h prime of 1. So I can add 2 equals negative a half h prime of 1. And now multiply both sides by negative 2. H prime of 1 is equal to negative 4. And therefore I can find both h of 1 and h prime of 1. And from here I could do other things as well. I don't have to, but for instance I could say, what's the tangent line? You know, because once you have the function and the derivative, you can do the tangent line. There's all sorts of things you can do. All right, but this is a good fundamental theorem of calculus mixed in with a little bit of, do we know what integral gives us 0? Okay. Number 12. Find the integral from 0 to log of 2 of the square root for e to the 2x minus e to the 4x dx. Okay, now I'm going to preface this by stating this one is definitely at the upper end of how challenging it might be. But, you know, it's good to challenge yourself. We like a challenge. I mean, that's why we take calculus, to be sufficiently challenged. Not too much, not too little, just the right amount. Okay, well, this function is not, it's not one of our 8. So we can't just integrate it right away. We've got to work a little bit. So we start thinking, is there some algebra or maybe something else we can do to help simplify this expression? Well, on the inside, both terms have an e to the 2x. So oftentimes a good thing to do is say, well, let me try pulling out common terms. So if I pull out here, let's see, we could have e to the 2x, then we'd have 4 minus e to the 2x. And we can take the square root of e to the 2x. That's not so bad. Square root of e to the 2x is e to the x. So you get e to the x, square root of 4 minus e to the 2x. So looking at this, we start thinking, oh, this is kind of feeling familiar now. Like we might be able to do something. We start thinking, what are some things we can do? Well, we're always in the back of our mind trying to say, where's the substitution? Where's the substitution? And the goal of substitution is to make substitutions that simplify your expressions. I think there's a substitution now that we can make. Do you see it? Notice this e to the x sitting there. If that were to be the derivative of something, because remember, we can look for a function on the inside or say, oh, I have something which I recognize as a nice derivative. This I recognize because it's a derivative of some nice function. What function gives you the derivative of it is e to the x? E to the x. So this is saying, oh, if we were to make du being e to the x dx, the good choice would be u equals e to the x. And you're like, well, yeah, but that says that the e to the x dx becomes your du. How do you handle the inside? Well, don't rain on my parade just yet. Let me see what we can do. We'll try it. Let's see what happens. So e to the x dx becomes du. What about this square root of 4 minus e to the 2x? See, e to the 2x, we've done this before, is the same as 4 minus e to the x squared. So it becomes the square root of 4 minus u squared. That's a circle. Do you know what circle that is? A circle of radius 2. So there's 2. Now, we're not done yet, because what haven't we done? We haven't done the bounds. So let's do our bounds. So if I have 0, e to the 0 is 1, which means we're going to start at 1. Okay, so we're starting here at 1. And then we're going to go to e to the log of 2, because I've got to put log of 2 in. Well, e to the log of 2 is 2. So we're going to go to 2. So that says we want that part of the circle. Okay, so that's cool. All we have to do is find that part of the circle, and life is good. All right, how hard could that be? And other famous last words. Okay, let's actually do a little bit of thinking here. This length here is 1. Do we know how high up this is? Can we find it? Well, be the square root of 4 minus u squared. So if u equals 1, be the square root of 4 minus 1, which says this is square root of 3. All right. Well, So I have this square root of 3 here. Now, why is that useful? Well, oftentimes we're going to say, look, we don't have a good antiderivative for this function. But we'll start thinking geometry. And here's sort of a nice fact about geometry. In fact, it's not sort of a nice fact. It is a nice fact. So suppose I have a circle, and I want to take a wedge of a circle. Maybe I'm visiting family, and we're like, well, let's get some pi. All right. They're going to say, well, how much of the circle do you want? Well, I want the central angle to be theta. And they're like, no, you got to tell us something better than that. You know, we don't deal that way. They're like, no, I want an angle theta. You got to tell us area. Ah, well, here, let me show this to you. If I want to find the area in that wedge, the circle radius r, it turns out there's a nice expression for it when you use radians. So here's the way it works. What you do is you think of the following. You say, well, how much of the circle have I taken? And the answer is, I can think of it in terms of the angle. It's theta over 2 pi, which is, if you want, it's the percentage, if you will, of how much the angle takes for a full revolution. Versus, I can think of it as the area of what's in the slice over the total area. That's the percentage of the area. So what you get is that the area of the wedge is, you multiply, is 1/2 times theta times r squared. So in this picture, what we can do is we can really think of it as sort of two things. And say, well, since it's not just a quarter of a circle, what I can do is I could come here. If I could figure out what this angle is, then I could figure out how much area is in this circle, and that would give me too much. But it would give me something. Then I would say, well, what's the too much? The answer is the too much is the triangle. And the good news is I know how to find areas of triangles. So now I just have to figure out what that angle is. So we go back. In fact, the angles involved are not just any angles. If you think about your trigonometry, you may have learned this triangle where you have a 1 here, a square root of 3 here, and a 2. Then the angles are, in this corner, pi over 6, and in this corner, pi over 3. And so, what's this angle? It's pi over 3. So that tells us this is pi over 3. Now, one way you can think about it is it turns out pi over 3, it's like a 60-degree angle, if you're more comfortable with degrees, which means that this wedge would be 1/6 of the whole circle. If you don't believe it, just plug in the formula. So you're going to take 1/2 times the angle, pi over 3, times the radius. Well, the radius is 2 squared. So this is the wedge. Then we're going to subtract the triangle. Well, the triangle has base 1 and height root 3. So 1/2 base height. So that's our triangle. So what do we end up with? Well, we end up with the 2 can cancel with one of the 2's there. So we get 2/3 pi minus 1/2 square root of 3. And that is our area. So we can use our geometry. Again, this is a case where use geometry. Now, I'm not going to say you're going to use geometry in every problem, but I would be on the lookout that it should hopefully appear at least one place somewhere on the exam. All right. Next problem. So let's let f of x be the integral 1/2 x squared minus 2 to 3/2 x of f of t dt. And here's the graph of f of x. It's shown here, shown below. And we want to determine the following. So we have 4 things that we have to find. F of -2, f of -1, f of 0, and f prime of 1. So let's just go through and work these one at a time. So let's start with f of -2. So we plug -2 in. So if we plug -2 in, that says everywhere you see an x, replace it by -2. So this will be the integral. 3/2 times -2 would be -3. Then we have 1/2 times -2 squared. Well, let's see, what would that turn out to be? Be 1/2 times 4, which would be 2, and subtract 2 is 0. So -3 to 0 of f of t dt. Okay, well that's fine. However, you got to be a little bit careful here. The bounds are kind of in the wrong order because they're from 0 to -3. We're more comfortable going from -3 to 0. So we'll flip the bounds and throw a negative in front. -3 to 0 of f of t dt. And now that we have that, we're ready to answer the question. It says start at -3, which is here, and go to 0, which is there, and find the area. Now, from -3 to 0, there's 2 pieces, and it's okay that it's not continuous. Just do each piece individually. You've got a little triangle, and you've got a rectangle. So, what happens? Well, we find the area in the triangle. That's 1/2. The area in the rectangle would be 2. So if we put that together, that's 2.5, or 2.5. And then remember that there's a negative because of the orientation, so this becomes -2.5. So that's part A. All right, part B. We want to find f of -1. So we plug -1 in. So let's see what we get. We get integral. -3/2 is our upper bound. We get 1/2 times -1 squared, which is 1/2. 1/2 subtract 2. Well, 1/2 subtract 2 is -3/2. And we're going to do f of t dt, which means we go to -3/2, which is here, and we start, and then we stop at -3/2, which is there. So what's our total? 0. So if it's the case that the upper and lower bounds match, it's 0. That's good. All right. Well, let's hope that happens more often. I suspect not. But you can always hope. There's maybe. All right. Now the next one. F of 0. So everywhere where I see x, I put 0. That's probably going to be pretty straightforward. So that would be what? Well, put in 0, you get -2 up to 0 of f of t dt. Now in that case, that's just the rectangle. And notice our orientation is perfectly fine the way it is. So what we're going to get is that our integral is matching the area of that rectangle. So we're using the geometry from the picture to help us answer these questions. So the amount of area, which is the integral, is 2. So really this is a problem where we do not try to actually find the piecewise function and try to integrate it. We're using the picture to help guide us. We're using geometry to answer these problems. Okay, one more problem, and we'll be done with this one. F prime of 1. Well, F prime, that tells us it's a test of our fundamental theorem of calculus. You should expect at some point during the exam, you will see a derivative of an integral in some way, shape, or form, possibly on more than one problem. Because after all, it's very fundamental to the topic. So make sure you're ready for it. So f prime of x, which is the derivative with respect to x of the integral 1/2 x squared minus 2 to 3/2 x of f of t dt is equal to f of 3/2 x times the derivative of 3/2 x, which is 3/2, minus f of 1/2 x squared minus 2 times the derivative of 1/2 x squared minus 2, which is x. So f prime of 1 would be the function at 3/2 times 3/2 minus the function at 1/2 minus 2, which would be minus 3/2 times 1. So we take our derivative, and now we plug in 1. So we go through and figure out what these things are. Well, our function at negative 3/2, we've actually seen this before. That's negative 3/2 is right there. And our function at negative 3/2 is 1. Our function at positive 3/2, well, 3/2, that's positive 3/2, that's 1/2. It's here. Well, this is on that straight line, y equals x. So this is 3/2. So we end up with this 3/2 times 3/2, which is 9/4, minus 1 times 1, minus 1. And so that becomes 5/4. And there's our answer. So these are fun. We like these ones because you can test all sorts of things. It's really testing geometry. Do you remember that if you need to swap bounds, you have a negative? Remember if you start and stop at the same point, you've got 0. Look for things like circles, triangles, rectangles, and piece it all together. And there you go. Okay. Ooh, a picture problem again. 2 picture problems in a row. They have to like us. Okay, set up integrals which will find the area for the region bounded by the curves y equals negative x. So here we'll go ahead and mark where these curves are. Y equals negative x is this curve. It's coming out. Y equals negative x. Y equals the square root of 6 plus x. So y equals the square root of 6 plus x is actually this curve on the top. And if you were to keep drawing this curve, what I would do is it would start coming down and come down here at negative 6. And y equals 1 over 25x squared. That's this curve right here. And if you say, that kind of looks like a parabola that's been squished down a lot, that's because it's a parabola that's been squished down quite a lot. So that's a good intuition to go to. And it says, they're very nice. Intersection points are at negative 2, 2. So that's over here at negative 2, 2, and at 10, 4. So we want to set up integrals which will find the area, and we're going to do it twice. So as integral, or possibly integrals, with respect to x, or in part B, with respect to y. So let's start with respect to x. Now, when we're finding area with respect to x, what we're thinking about doing is we're integrating our height dx from a to b. So the height, this is top minus the bottom. And what you should always think of, and this is going to be a theme going forward into Calculus 2, which is that integration works by breaking things into pieces, and we're breaking pieces up into little bits of area. So the height is not the area, but when you take a height times a little tiny change in x, that's a height times a width. So height dx is actually the area of a small sliver. And then the integral sign, it basically says you're adding stuff up. Think of the integral as being that long stretched out s. Long stretched out s for adding things up. Throwing up all these little pieces. Now, what you do is you say, okay, what I'll do is I'll just figure out what is the top minus the bottom. Now, you have to be on the lookout for, does this ever change? And if the answer is yes, if it changes, that says break your integrals up, because you always want it to be consistent. So as we start, we say, okay, top minus bottom. We see the square root of 6 plus x is the top, negative x is the bottom, but then a change happens, and it happens right here at 0. And at 0, what happens is that while the top remains the square root of 6 plus x, the bottom switches to 1 over 25x squared. So that we have two different behaviors depending on where x is at. So we're going to have to do two integrals for part A. So the first integral, we say, all right, is the part on the left. And we say, where do we start? Well, the left point starts at -2. We're going to go to where we have a change in behavior, which is 0. So -2 to 0. Then the top curve, square root of 6 plus x minus the bottom curve. So minus x. And this is just, you'll notice here, is the problem doesn't say to find the area. The problem says set up. So if you might see a problem that says set up, but do not evaluate. It's one of the sweetest sentences that a calculus student encounters. It's like, my favorite phrase, do not evaluate. You see that a lot more in Calc 2 and Calc 3, where you get things which are just like, these are crazy to evaluate. Don't even think about it. Okay, for the second half, we start where we have our new behavior, which is at 0, and go to our far right point, and that far right point is at 10. So 0 to 10. We still have the top curve as square root of 6 plus x. Now our bottom curve, subtract 1 over 25 x squared dx. And we're done. Let me take advantage of this particular moment to point out that if you, at any point during the exam, forget the dx, and you're just like, yeah, I know what I'm doing, I don't need it, you will lose a point. Because we are very particular about notation. That dx is not just there for show. It represents something. And so make sure that throughout the exam, you're using good notation. I know you're the good students, but still, I just want to warn you, because I want to make sure you do well. Now we're going to switch gears, and we're going to talk about integral with respect to y. So that's part B. Now, the way we're going to switch gears is we actually have to go through and think about the curves. Currently, the curves have been written in the form as y is a function of x. I need to rewrite them x as a function of y. Because what's going to happen is I'm going to integrate from different y values, c up to d, and now I'm not integrating height, I'm integrating width. So width dy. And how do you find width? Well, width is you take your right minus left. And same principle is in effect. If you ever change your right or your left curve, you've got to split it into two integrals, or possibly even more. So we're thinking about slicing in essentially a horizontal way is what it turns out to be. And you can see at the bottom that the two curves are consistent. It's this straight line on this side, this squished parabola, up until right there. And then there's a change in behavior. And then there's a different integral. So we're going to have to do two integrals. All right, so, sorry I got sidetracked. Let's get back to our business at hand. We need to rewrite these in terms x as functions of y. Well, y equals negative x, that's not so bad. That becomes x equals negative y. Y equals 1 over 25x squared. Well, multiply by 25. 25y equals x squared. And then take the square root. X equals square root of 25y. Or if you like, that could be 5 square root of y. Now you might say, oh, wait a second, you forgot plus or minus. Okay, good point. It could have been plus or minus, but notice that we're in the place where x is positive. And therefore we're in the positive side. So it is definitely the plus side. For this last one, you square both sides. Y squared equals 6 plus x. And then you can move it, the 6 across. So x equals y squared minus 6. I can say these words. Okay, so here we go. So the first integral, we start at the very bottom, which is at y equals 0, and we're going to go up to the first y where we change behavior. The y where we change behavior is at 2. So 0 to 2. Then we're going to take our right curve, which is 5 root y, subtract our left curve, which is negative y. So 5 root y subtract negative y dy. Then we're going to add to that. Now we go from where we changed behavior, which was at 2, up until the top. And we end here, we can see the y value is at 4. So 2 up to 4. The right curve is still 5 square root of y. And then we're going to subtract. The left curve has changed into y squared minus 6. And that's dy. And so there's our two answers. There's part B, and I guess I should have marked this is part A. All right, and we're done. These are actually integrals you can do, and you'll look at them and say, they don't look the same, and they're not as far as the setup goes, but the answers will be the same. So, all right, moving on. The controls for Scott's bots are not working. The acceleration is fixed to be acceleration of t is 2 minus 6t yards per minute squared, where t is measured in minutes from turning on. Now, given we need the position and velocity to be 0 at time t equals 2 minutes, determine the position and velocity at time t equals 0. So we somehow, this machine has broken, and we need to somehow make sure we can land it safely at 2 minutes. So we need to, so that time 0, it's not moving up or down, velocity is 0, and it's actually at ground level. So what's happening here is, what do we have? Well, we need our position velocity to be 0 at time t equals 2 minutes. So this tells us that we want to have velocity at 2 equals 0, and position at 2 equals 0. So that's information we're given that this is what we want. So what do we want to find? Well, the question becomes, what is the velocity at 0 and what is the position at 0? So we have two pieces of information here and our acceleration, and we want to use that to determine other pieces of information at a different time. So we start at this problem. We say, all right, acceleration and velocity and position, they have nice natural connections. So in particular, if I start with acceleration, if I want to get to velocity, I would take the antiderivative. So that would be 2t subtract 3t squared plus some constant c. Now we say, well, we have information about velocity, so that v of t equals 0, we can use this to solve for our c. All right, so how do we do it? Well, we get that 0 needs to be velocity at 2, which will be 4 minus 12 plus c. So that tells us we need c to be 8, because I can solve for c. So we can update. That says our velocity at any given time needs to be 2 times t minus 3t squared plus 8. In particular, I can now find the velocity at 0. So the velocity at 0 will be 8. So that's what we need. Now, it didn't ask us for units. If it did, we could find it. It's 8 yards per minute. Okay, well, that's just one layer. We need to also do position. So we integrate velocity to get that position is t squared minus t cubed plus 8t plus some other constant. I'm going to call it d. The reason I don't want to use the same constant is that it's going to not necessarily be the same value. So I don't want to get confused by that. So we do what we did here. We say, okay, I know I need to have 0 equals the position at 2. So we plug in 2. We get 4 minus 8, and then plus 32 plus d. All right. So, well, what does that give us? Oh, wait. Plus 16. Yeah, 32 seems excessive. Okay, yes. 4 minus 8 plus 16. All right. Well, what is that? Well, that says 20 minus 8, d equals negative 12. Okay, so our function s of t becomes t squared minus, see, that's the danger when you can't read your own handwriting. Be careful, be careful. You're probably thinking, that would never happen to anybody. No, it happens. All right, so what's our position? Well, at time 0, plug in 0, you get negative 12 yards. Well, maybe it's in, like, say, a deep theater or something. So you might have position be negative. That's okay. That's all right. And there's our answer. Okay, good. Number 16. We're getting closer to the end. The end is near. The end is near. Rewrite the following as some number c times the integral from some number a to some number b of f of t dt for appropriate choices of a, b, and c. So what we want to do is we want to rewrite these integrals, and we want to get them to sort of be compatible in some way. So we're going to go through, we have 4 pieces. We're going to work one piece at a time, and let's see what we get. So let's start with the first one here. Well, I want to make this inside bt. Right now it's negative x. So that's easy enough to do. I'll just set, let's let t equal negative x. I can do that. What would dt become? Well, minus dx. Yes? No? Maybe? It does. It works. So I can move the minus across. So I can say that minus dt equals dx. So if we do this, what do we get? Well, we'll get an integral. We update the bounds. So instead of going from negative 2 to positive 1, what will happen is I'll go from minus minus 2, which is 2, up to negative 1. And then I'll have the 2 stays in front, but then there's a minus attached to it, and it becomes f of t dt. But we don't like the bounds being flipped this way, so we'll use the negative there again and flip it back. So 2, integral negative 1 to 2 of f of t dt. So that's a way to write the first integral in something that's a little bit simpler to work with. Well, 1 down, 3 to go. Let's go to their second integral. All right, integral 8 to 64 f of y to the 1/3 over y to the 2/3. What can we do here? Well, again, we want our inside. Let's make it look like t. So let's just set t equal y to the 1/3. What would dt be? Well, pull down the 1/3, y to the minus 2/3 dy. And we can do a little bit of fancy multiplication here. This 1/3 I'll move across as a 3. Now notice that y to the negative 2/3 dy is actually sitting there very conveniently, ready for us to pounce. So what does this become? Well, we're going to get a 3, so I'll put that out here in front. That's a constant. The f of y to the 1/3 becomes f of t, and then the y to the 2/3 on the bottom times dy becomes our dt. So of course at 3. Now about the bounds. Well, we have here 8. What is the cubed root of 8? It's 2. Then we have 64. Cubed root of 64 is 4. So we have 2 to 4, and then we have a factor of 3, f of t dt. All right, that's our second one. Now we come to our third one, and that's weird. Because again, you might say, okay, no problem. We just say, let's let t be z squared, but there's no 2z to match with. And then we have this arctangent. Now, I like arctangent, but that just seems really hard to integrate. This is a really weird function here that they've given us, a very peculiar function, unusual, not typical, something strange. You might even say this function is odd. Oh, it's an odd function. Now, what does an odd function mean? Well, an odd function is a function with symmetry. So if you think about an odd function, it's a function that would have this type of behavior. And in particular, if you plugged in negative x, it's the same as if you did the negative of just plugging in x. Now, what's nice about an odd function integration is that if you're integrating from negative some number to positive some number, you'll get cancellation. Notice we're integrating from negative 5 to positive 5. So we just have to convince ourselves this is an odd function. Now, because of the squaring, it doesn't matter if you plug in a positive z or a negative z on the inside here, you'll still get the same value. And arctangent is an odd function. So this is an odd function. We're integrating from negative 5 to 5. So this integral simplifies to 0. The most complicated thing becomes the easiest to work with. Who would have thought? Well, somebody did. Somebody wrote this problem. Okay, last piece here. Let's see what happens here. Well, again, we want the inside. So we'll set t to be 2 sine theta. What's dt become? Two cosine theta d theta. And we do have a 2 here, which we can really pull in if we wanted to. So we do have a 2 cosine theta d theta. So that's good. So we get an integral f of t and a dt. Now we've got to figure out the bounds. Well, we plug in negative pi 6. Sine of negative pi 6. Do we know that value? It's negative a half. Then we double it. Gets us to negative 1. Sine of pi halves times 2. Do we know that? Sine of pi halves is, sine of pi halves is 1, and double gives us 2. All right. So we really have, after we make appropriate substitutions, those pieces added together. I guess I should have put the 0 down here. And we see, wait, the first and last piece match up. So I can put those together. So it's like I have 3 integral negative 1 to 2 of f of t dt plus 3 integral 2 to 4 of f of t dt. Well, they're both 3's. They're both f of t dt's. The only thing is that one goes from negative 1 to 2, one goes from 2 to 4. So we can write it as a single integral from negative 1 to positive 4 of f of t dt. And there's our answer. Woohoo! Fun. This is really testing us on our ability to carry out substitution and rewrite integrals. And then there was a little bit of symmetry thrown in the mix, which is always a fun thing to do. It's always fun to have a little bit of symmetry thrown in the mix. All right. A particle has acceleration. A of t is 4t plus 4 divided by t squared plus 2t plus 2 quantity squared. And at time t equals 0 is located at 0. As time heads off to infinity, the particle moves, but not very far. It's going to move to some finite location. Part A says find the velocity of the particle at time 0. And part B, where is it moving to as time goes to infinity? And there's a hint that says if you're stuck, try completing the square. Well, that's an unusual hint. How would we be stuck? Psh, silly hint. All right, well, let's begin. So we have our acceleration. We were trying to understand something about velocity and location. So we just did a problem similar to this. So we're probably going to do something similar as we did before, which is let's talk about integration. Okay, so 4t plus 4 over t squared plus 2t plus 2 quantity squared. So velocity of t is the antiderivative of this expression. So we start thinking about, well, what are some things we can do? Well, it definitely is not looking very promising right now. It's not on our list of 8. So let's start by looking for a good substitution. And I think a good candidate is the stuff that's on the inside down below. Seems a reasonable place to start looking. Let's see if it works. U equals t squared plus 2t plus 2. What would du become? 2t plus 2 times dt. And check it out. 4t plus 4 is basically double that. So, if we use that substitution, then the upstairs becomes twice du. So I have a 2 du, and then the downstairs becomes u squared. If we write that in our calculus language, that's u to the minus 2. So now we can integrate this. And if we integrate that, well, you add 1 to the exponent. So that would be u to the minus 1. We still have the 2. Then we divide by that exponent, which means put a negative in front. Then, of course, add in a c. And so we have, this becomes minus 2 over t squared plus 2t plus 2 plus some constant c. Now we need to find the velocity of the particle at time 0. And I don't think we really have that much information at time 0, because our information says location at time 0, and what happens as time goes to infinity. So we don't yet know what c is. Well, so that's okay. We just do it a second time. It was successful the first time. I'm sure it'll be just as successful in round 2. So we begin round 2. So we have our position, s of t is going to be integral of negative 2 over t squared plus 2t plus 2 plus c. Now, the good news is part of this is pretty straightforward to integrate. There's 2 terms. The plus c is pretty straightforward to integrate. If you integrate that, you'll end up with a c times t plus, there'll be another constant d at the end. But then we still have this other stuff here. I'll pull the negative 2 out. 1 over t squared plus 2t plus 2 dt. That part is not so obvious what to do. I mean, you can try, u equals t squared plus 2t plus 2 again, but the problem is we don't have the part upstairs that would give us what we need. So that part, that kind of substitution, it's not going to work this time. So we have to find a different idea. Okay, what can we do? What can we do? I don't know. I'm feeling a little stuck. Oh, there's a hint. Are you stuck? Try completing the square. Okay, let's see. Is there a square here? I see a square there. T squared plus 2t. What would I need to add to t squared plus 2t to make a square? T squared plus 2t plus what makes a square? If you add 1 to t squared plus 2t plus 1, what do you get? You get t plus 1 quantity squared. Now you might say, wait a second, you have plus 2. Well, that's okay, plus 1 more. So the denominator is really t plus 1 squared plus 1. Well, can we integrate that? Well, you could, and if you're not comfortable with it right away, let's do a substitution. W equals t plus 1. If we make that substitution, what is dw? It's dt. So this becomes the integral of 1 over w squared plus 1 dw, and that's on our list. So it's arctangent of w plus some constant. So it becomes arctangent of t plus 1. So we now have the following. Our s of t is equal to negative 2 arctangent of t plus 1 plus c times t plus d. We are given two pieces of information about position, so let's use those two pieces of information. At time 0, we're at position 0. So we plug 0 into this expression. So we get that 0 is equal to negative 2 arctangent of 1 plus c times 0 plus d. Well, that lets us solve for d. What is arctangent of 1? Pi over 4. So if you times that by 2, that gives you pi over 2. So that tells us that d has to be pi over 2, because remember, we're going to take it across. All right, there's another thing that has to be true. As time goes to infinity, the particle moves to a particular location. Now, let's look at this expression and think about what happens as time goes to infinity. Well, the d is a constant. That's not going to do anything as time goes to infinity. Arctangent of t plus 1, well, arctangent has an asymptote. So it's going to approach something as time goes to infinity, so that's going to be fine. But c times t, it's going to get huge unless what's true about c? How can I make sure this doesn't get huge as time goes to infinity? Yeah, the only way this needs to be bounded as t to infinity, which means that c has to be 0. Because if c is not 0, it's not going to stay put. It's going to get arbitrarily far away from where you began. So we've now figured out c and d. And with that, we can answer some of our questions. So for instance, we can go back and say, what's the velocity of the particle at time 0? Well, see, this is our velocity. We just figured out that c is 0. So here's our velocity function. And if we plug in 0, what do we get? Well, negative 2 over 2, which is phi of 0 is negative 1. Part B, where is the location as t goes to infinity? Well, our location is we have negative 2 arctangent of t plus 1. So, okay. So t goes to infinity for, is that on this? Yeah, of s of t. What do we have? Well, we get, essentially, we're going to negative 2 arctangent of infinity plus pi halves, right? Now, of course, you should rightly object, say, hey, Steve, there's no such thing as arctangent of infinity. You just made that up. Yeah, I did. Okay. But the idea works. So when we're talking about arctangent of infinity, what's happening to arctangent as you head off to infinity? What does arctangent approach as you head to infinity? Pi over 2. It's a horizontal asymptote. It comes from the vertical asymptote of tangent. So we get negative 2 times pi over 2, which means it's going to negative pi plus pi halves. So the answer is, where is it moving? It's going to negative pi halves. There's the answer for part B. This one is definitely non-trivial. So this would be on the really upper extreme of how hard it would get. Probably even maybe slightly harder than what we'd want to give you on the exam. But you should see challenging problems. You get stronger the more challenging the problems you get. All right, which brings us to our very last problem. And I know we've already had a lot of fun, but let's finish it. Let's do this. Find the average value for f of x equals 1 plus 2x e to the negative x all over 1 plus x squared e to the negative x for the interval from 0 to 2. Now, this one is one of those ones where once you see it, you're like, aha, I see it. Life is good. And if you can't see it, you're like, ah, and you're frustrated. I suspect if I showed this to some of the graduate students, they would fall into the, I'm frustrated category. But we can do it. We're good people. So first off, average value, we see average value, we know it means it's an integral. We're going from 0 to 2, so it's integral from 0 to 2. We're going to divide by 1 over 2 minus 0, and it's the integral of our function. Now this function is not on our list of 8 functions we can integrate. So we aren't going to be able to do this function right away. So we think, okay, what can we do to this function? We're trying to look for clues of things we can do. Now, there's kind of a clue that I spot, which is here. See, there's this x squared, and I see a 2x right above it. And I say, well, this denominator looks a lot like the numerator, but that x squared, if I took the derivative of x squared, that gives me 2x. So it's somehow suggesting, oh, if I make a good substitution, then I should get the derivative of the bottom be the derivative of the top. Well, that's not currently the case, because if you think about it, if you take the derivative of 1, that would go away. It would be 0. So it says, okay, somehow we want to rewrite it so that if we end up with taking the derivative of the bottom, it'd be the top. And in particular, if this e to the negative x weren't attached, then I just have x squared, and the derivative of x squared is 2x. So I asked the question, is there a way to get that e to the negative x unattached to that x squared? And how can we do it? Well, one way to do it is to say, let me cancel it off. To cancel e to the negative x, I can multiply by e to the x. So I'm looking for ways to rewrite my expression. So this is an algebra idea. So if we multiply by e to the x top and bottom, upstairs we get e to the x plus 2x. Downstairs we get e to the x plus x squared. Now we're like, okay, this is looking promising. The derivative of x squared is 2x. What's the derivative of e to the x? E to the x. What? This is like, it's almost like they wanted us to do this integral. If u equals e to the x plus x squared, du is e to the x plus 2x dx. So this would become 1/2 integral of 1 over u du. Let's do our bounds. At 0, e to the 0 plus 0 squared, 1. At 2, e to the 2 plus 2 squared is e to the 2 plus 4. Can't really do much about that. Well, what's the integral of 1 over u? It's 1 over 8. ln, yeah, natural log. Natural log of u, evaluate from 1 to e squared plus 4. Well, the nice thing about natural log of 1 is that's 0. And so our final answer is 1/2 natural log e squared plus 4. And we're done. Because that was our last question. All right, so just remember, if you're thinking about integration, antiderivatives, always check, is it one of my basic formulas? Can I rewrite it with algebra or trig? Look for a substitution. And these are your basic ones. If it's not on this list, don't try to be creative. You know, this is not art history. You don't get points for creativity. You're going to lose points. So just be careful, do well, and good luck on the exam.